Hello, welcome to today's video. Today we are looking at transformations, specifically transformations in the y direction. And when we're doing that, we're going to look at how that affects equations, how that affects the coordinates, and little strategies you can use to help you spot when a transformation has happened. So let's get into it. To kick things off, the first thing I guess to mention is what is the general idea? What are we trying to do? Well, all y direction transformations are all applied to the graph or the sort of the function of x as a whole. So we're obviously used to dealing with equations that are generally of the form y equals f of x most of the time, and that's what we're going to be basing all the examples in this video on the assumption of the assumption that they're of the form y equals f of x. But therefore that means is all y direction transformations are applied treating this function as a one big whole thing. Almost like you can imagine yourself putting brackets around that entire function and then applying that action to those brackets. So in some ways that does make it quite easy to spot them from a certain point of view, because you're just looking for an action that's happened to the whole algebra, or if not to the whole algebra, it's in a fairly logical way. The other thing to mention is y direction does fairly straightforward things in terms of the numbers you see happening in effect in the equation are what's actually happening in the transformation in the words, and then also what actually happens to the coordinates as well. So that does make things a bit easier to spot. Right then, okay, so getting on to things, let's start off with translations. So the way we're talking about, if we're talking about a y direction translation, is we're talking about a translation by the vector 0 and then whatever you're translating by, let's say b. And that's the best way to word these transformations. There are ways you can word this 100% with words, but I wouldn't recommend that when if you can just write a vector like this, column vector, saves a lot of words. So, hey, take the easy option. In terms of applying it, well, from the notation point of view, what we're doing is we're taking f of x and then we're just adding on whatever we're translating it by on the end. So, I mean, by all means, you can have the brackets there and treat it like that, but of course, adding stuff onto brackets is kind of, as if the brackets almost aren't there. So, doing some examples, let's say we had the graph y equals x squared minus 5x plus 2, and we were doing a translation 0, 10. Well, all you'd have to do is you'd have to do x squared minus 5x plus 2 plus 10. And that's all there is to it. Of course, you could then simplify that, and then your final answer would be that. So the key thing to spot with y direction transformations is or y direction translations, I should say, is you're looking for the constant to have changed. It's only the constant that would have changed. Originally it was 2 in the original function, and after we've done the translation of plus 10, the constant's gone up by 10. All the x terms, they all stay exactly the same as they are. That's the only thing that's changed. So that's how you can spot them. And then as far as the coordinates go, well, it's fairly logical. Whatever you're doing in the translation, in terms of the notation up here, sorry, I lost my voice for a second there, then that is what's going to happen to the coordinates as well. So if, for instance, we're doing a translation of, I don't know, let's do a minus 1 this time, 0, minus 3, and we're applying it to the point 4, 7, and what happens? Well, first thing to point out is the x coordinate doesn't get affected at all. All y direction transformations are only affecting the y coordinate. And all that happens is, well, we literally subtract 3 from the y coordinate. So after the transformation, it would just become 4, 4. Because 7 take away 3 is 4. So that's all there really is to it as far as the y direction translations go. Okay, the next one up is stretches. Now, there's two ways you can word these. You can either word them as a stretch scale factor, we could say k, stretch scale factor k, parallel to the y-axis. So that's one option for the wording. The other option for the wording is to say a stretch scale factor k. Again, that's just a placeholder for whatever the actual scale factor is. But instead of parallel, almost wrote the same thing again twice, you say in the y direction. Now, the trouble is with me writing both these things is students often end up doing a mishmash of these two wordings and say a stretch, scale factor, whatever, in the y-axis. And you can't say that. You can't say it because it doesn't make sense. It's not actually saying what it's actually doing. And you might say, but why? It's only one word. Why does it matter? Well, have a think about what the word in means. A little analogy here for you. If there's a house, right, or a building, and there's you outside of the house, and you wanted to go in the house, where are you going to head towards? You're going to head towards the house. So the thing you're trying to head into is the thing you're heading towards. So you'd be going towards the house. When we're saying a stretch parallel to the y-axis or a stretch in the y direction, if we have the y-axis, then what we're saying is the stretch is happening in this direction, up and down. If you're saying stretch in the y-axis, what you're effectively saying is you're saying you're heading in that direction, towards the y-axis, which is not what we're doing. So that's why it's pernickety, but when you think about it, the words, it actually does make sense why we can't say in the y-axis. Okay, actually applying it, how to apply it? Well, basically it's a multiply. And just like, as I said before about y direction transformations, they're applied to the function as a whole. So what we'd do is we would take out f of x and literally multiply it by that scale factor k. And if your function has lots of things in it, then you've got to put the brackets around it and make sure then when multiplying out the brackets, everything that's meant to be multiplied gets multiplied as appropriate. So, for instance, an example we could have, again, we could use the quadratic. I quite like that as an example. Y equals x squared minus 2x plus 5. That's a different quadratic to last time, but that doesn't matter. And we're going to stretch it, scale factor, let's say 4, parallel to the y-axis. What that'll do is it will mean we're going to take the entire function that we had before, x squared minus 2x plus 5, put it in brackets, and then multiply it by the scale factor, which is 4. So I'm just going to put a 4 in front of those brackets. And once again, then how do you simplify it? Well, it's just however the action interacts with the brackets, which for multiplying means you've got to multiply every individual thing separated by a plus or minus inside by that number. So it's going to be 4x squared minus 8x plus 20. So therefore, the way of spotting if a stretch parallel to the y-axis has happened is you're spotting for every individual thing in your, or every term in your function to have been multiplied by the same number. It's got to be the same number. If different things have been multiplied by different numbers, that means it's not a stretch parallel to the y-axis. Okay, the last one to look at that we need to look at is a reflection. Now, we're talking about y direction transformations, and this one we're going to lump in with the y direction transformations is a reflection that's abiding by that, but we don't call it a reflection in the y direction. We call it a reflection in the x-axis. Now, that does kind of go against what I was saying earlier about we shouldn't use the word in something axis, but that's because actually in this case it does make sense. Because when we're doing a reflection in the x-axis, what we're saying is if we have some coordinate axes, it means we're saying we're using the x-axis as the mirror line, the reflection line, which means that we actually are reflecting in the x-axis because the movement, if we have a graph that looks like this and reflect it in the x-axis, it's going to become something like this. Obviously, that's not a perfect drawing, but you get the idea. And therefore, the movement has happened up or down. In other words, towards the x-axis. So that's why we're allowed to use the word in this scenario, but what weren't for stretch. So there you go, that's the wording. Now, as for applying it, the best way to view a reflection in the x-axis is it's a stretch scale factor -1 in the y direction. Now we can't call it that because that's not specific enough, but that's what it effectively is. So basically, same idea as how you apply a stretch in the y direction, taking the entire function and multiplying it by something. It's just in this case we're multiplying it by specifically -1. Now, it's worth mentioning that if you get something other than a different negative number being multiplied, that technically isn't just a reflection anymore. It's a combination of a reflection and a stretch in the y direction. Because we generally avoid, I didn't mention that before, we generally avoid having a stretch with a negative scale factor. Okay, so therefore, applying that, if we have, again, we could have a quadratic. This time we will have the same one as last one. And if we're doing a reflection in the x-axis to it, then after that, all that's going to happen is we're going to write y equals entire function in brackets, and we're multiplying it by -1. And as before, just deal with the brackets as you normally would, multiplying them out. So that'll be -x squared plus 2x minus 5. So spotted in much the same way that stretches can be spotted. Now, something to point out I forgot to do before, the coordinates. How are coordinates affected? I didn't mention that before. What happens if we have, for instance, the coordinates, let's say 4, 9, and we want to do a stretch scale factor, let's say, I don't know, let's say 5 parallel to the y-axis. Once again, the wording gives a clue of what we're doing, as well as the action we actually did to the function. Stretches is a multiply, so if we got a stretch scale factor 5 parallel to the y-axis, that literally just means we're going to multiply the y-coordinates by 5. X-coordinates, it's a y-direction transformation, so they're not going to change. It's just the y-coordinates. So 9 is going to get multiplied by 5 to get 45, and then boom, that is your final answer. So therefore, if we look at how coordinates are affected when we do a reflection, it's a very similar idea, but we're multiplying by -1 instead. So if we have the coordinates 4, 9 again, and we do a reflection in the x-axis, then therefore, after we've applied that action, we're going to multiply the y-coordinate by -1. And there we go. That would be how the coordinate gets transformed. Okay, those are the 3 types of y-direction transformations that you need to know. They can all be spotted because you're doing something to the function as a whole. Now, as I said, technically with adding, that doesn't really kind of show because you are only affecting the constant as a result. But that's just due to how adding works with brackets, basically. Right then, the other thing to mention is, as I said, the wording in the description for the transformation, for y-direction transformations, does give a fairly good reflection of what's actually happening to the function. So a stretch scale factor 4 means we do end up multiplying by 4 in the actual when doing the function, and then definitely reflects what happens with the coordinates. Okay, hopefully that was useful, and I'm sure I'll see you in a future video, possibly on the x direction transformations.